Imagine this. You're in the cockpit, guiding a sleek jet through the clouds, maybe flying from, I don't know, a busy coastal hub like LAX, heading towards somewhere mountainous inland, say Denver. You glance down at your altimeter, that absolutely vital instrument showing your height. But what if, just what if, that crucial number isn't telling you the whole truth? What if it's off, even by just a little bit? Below you, those peaks, maybe the Rockies, could be looming closer than you think, or maybe even more worrying, another aircraft might be right there in your airspace, thinking they're at a safe, separate altitude. The stakes in this kind of scenario aren't just high. They are, well, quite literally about life and death in the sky. Welcome to the Deep Dive, where today we're diving headfirst into the absolutely critical, yet let's face it, often misunderstood, world of altimeter setting procedures. This isn't just some, abstract theory lesson. This is about the fundamental pillars of air safety. It's about the precise science and the solid procedures that make sure aircraft don't collide with terrain or, maybe even more complexly, with each other up there. And for you, our listener, especially if you're deep in preparation for those ATPL theory exams, this deep dive is absolutely for you. Our mission today is to take what often feels like a dense, jargon-heavy subject and really break it down, make it crystal clear, actionable knowledge. We're going to clarify those pivotal concepts like transition altitude, transition level, and exactly how aircraft communicate their vertical position. We want to make sure you not only grasp the material, but you can confidently answer those tricky exam questions and really understand the safety behind it all. We'll pull out the most important bits, highlight the crucial details, and make sure this information, well, it sticks. So buckle up and let's get started. Okay, building on that vital groundwork, let's really get into why setting that altimeter subscale correctly is just so incredibly important. It sounds technical, maybe a bit dry, but like we said, it's fundamentally about safe passage. What are the core reasons this seemingly small adjustment carries so much weight?
That's really the perfect place to start because the core objectives, they're remarkably clear, actually, despite the atmospheric complexities involved. There are basically two main goals. First, making sure you have adequate terrain clearance, always, especially during departure and arrival, those dynamic phases. And second, providing adequate vertical separation between aircraft once you're airborne and away from the immediate airport environment. What's quite sobering is that aviation history, unfortunately, has examples, accidents directly linked to getting these settings wrong. Controlled flight into terrain, CFIT, that's often where a perfectly good plane is flown into the ground or an obstacle, sometimes because of positional awareness issues, which can definitely stem from wrong altimeter settings. It's a stark reminder, really. While ATC gives crucial guidance, the ultimate responsibility, the final say on safety, always rests with the pilot in command. Always.
Okay, so let's unpack that first one. Terrain avoidance. You said during instrument departures or arrivals, the aircraft follows a published profile. How exactly does the altimeter setting ensure we don't, have an unscheduled meeting with a mountain, especially somewhere like the Rockies approach we imagined?
Right, that's where the local pressure setting is absolutely paramount. The core idea is this. Until the aircraft climbs above an altitude that's considered safe in all cases,
Right.
basically high enough to clear everything around its altimeter must be referenced to mean sea level. No exceptions. Why? Because all the obstacles shown on approach plates, departure plates, all those required altitudes in the procedures, they are universally referenced back to sea level. Think of it like a common starting point, the ocean's surface. And because sea level pressure, which we call QNH, changes with weather and location, and avoiding terrain is inherently a local problem, your altimeter reference has to be the local QNH. That specific local reading ensures your altimeter shows your true height above mean sea level right where you are, giving you that precise picture of terrain clearance.
Okay, and just to be absolutely sure we're clear, what exactly is QNH then? What's the practical result when a pilot sets it correctly?
Good question. QNH is defined as the barometric pressure they actually observe at an aerodrome, which is then mathematically adjusted using the International Standard Atmosphere, or IS, pressure lapse rate to show what that pressure would be if you measured it right at mean sea level. Now, IS pressure lapse rate sounds technical, I know, but basically, ISA is a...
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.